While mean, median, and mode are great descriptors of data, it is important to not ignore the shape of your data. Variability around the mean can be biologically important. The true population parameter is somewhere within the variation around our estimated sample mean. Variability can be measured in multiple ways, including the range, which is the difference between the largest and smallest values. Interquartile range, and that's the difference between the 25th and 75th percentile. And you have variance and standard deviation, which are the differences between a random sample and the mean. And the coefficient of variation, a measure of the standard deviation that is independent of the mean. Box plots can be used to show ranges. Range is the difference between extreme values. It is a basic measure of variation, but is biased on sample size. Smaller samples tend to give lower estimates of range, and larger samples tend to give higher estimates of range. The interquartile range is measured by sorting the data such that the individual in the middle is the median, and the first and last individuals are the highest and lowest. The other two quantiles are the individuals at 1/4 and 3/4 the way into your sorted list of data. The difference between these quantiles is the interquartile range. We can also measure variation more eloquently by calculating variance and standard deviation. Both of these measure how far individual observations are expected to deviate from the mean, because the differences between all observations and the mean sum to 0. Standard deviation variance work from the squared difference between observations and the mean. We call this the sum of squares. So first, let's talk about variance. Variance is the expected squared difference between an observation and the mean. The parameter estimate is sigma squared equals the sum of the observed value of each ith individual in the population minus the population mean squared. The estimate of variance is s squared equals the sum of the observed value of each ith individual in the sample minus the sample mean squared. We call the numerator in both of these the sum of squares. Standard deviation is simply the square root of the variance. The parameter is sigma, and the estimate is s. I have included here the long-form calculation for both sigma and s. We will be calculating standard deviation and variance quite a lot in this course, so you need to make sure you understand how to do these calculations. This is now a good time to discuss some important rules for rounding, as calculating mean, variation, and standard deviation, as well as many other calculations we're going to do in this class, can return values with precision that exceeds biological interest. For example, a number like 1.25 centimeters can be biologically significant. However, a number like 1.253466643 blah 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 centimeters loses meaning after a few digits. A good rule is to round these larger numbers by a reasonable number of significant figures. Presenting 1 or 2 more digits than initially measured is a good guideline. So, if we measured to the nearest 1 centimeter, we would round the larger number to 1.25 centimeters. Note, do not round while doing intermediate calculations. Round only the final results of the specific summaries of interest.